So, hello everyone. I am Semra. I am a PhD student at the University of Edinburgh, and today I will present part of my PhD research. So, first, to introduce the motivation for this work, heating represents a major share of energy use in the UK, and it is still dependent on fossil fuels. And at the same time, we are continuously losing significant amounts of low grade waste heat from sources like data centers and industrial applications because the timing of heat supply and heat demand doesn't always match, and this creates a strong need for seasonal thermal energy storage solutions. And one promising opportunity for that is the use of flooded abandoned coal mines, as you also know. However, mine thermal energy storage systems are relatively underexplored. So there is a lack of understanding of how these systems might perform over long time periods. So based on this gap, the objective of this study is to evaluate the feasibility of using mines as seasonal energy storage mediums through numerical modeling. So to do that, we defined the hypothetical case study here. Starting from the heat source, we have considered a constant thermal output of 1 megawatt throughout the year, representing a low-grade waste heat from a data center. And the heat demand is generating using the heating degree day method based on the climatic conditions representative of Glasgow. And as expected, the demand is significantly higher during winter months and much lower during summer. And based on the mismatch between the constant heat supply and the highly seasonal demand, we conceptualized this system as seasonal thermal energy storage system. So excess heat produced during the summertime is going to be stored into the mines, and later during higher demand, this will be extracted. So in this slide, I've tried to explain the simulation setup and operational strategy used in this study. So in terms of well configuration, although more complex systems are possible, we have adopted a more simplified approach with one warm well and one cold well. And the operation follows a seasonal cycle in here with 6 months of heat injection during summer and 6 months of heat extraction during winter. And temperature, and this cycle simulated over 10 years. And a temperature difference of plus and minus 5 degrees relative to the ambient mine water temperature is applied to define the injection temperatures in the model. And in terms of injection and extraction flow rates, these are derived from the monthly heating demand, the plant temperature difference, and an assumed heat pump COP of 4. So the upper plot is the resulted flow rate distribution, but in the model, for simplicity, these flow rates are applied as an evenly distributed profile while preserving the total energy input to the system. So here we have the model overview. I've tried to explain the coupled thermohydraulic framework here. The subsurface here is represented using a hybrid approach where different components are modeled at different dimensions to balance physical accuracy and the computational efficiency. Here, mine galleries are modeled as one-dimensional features, treated as fully open conduits, where non-isothermal pipe flow module is used to capture both fluid flow and heat transport. And for the mine panels, they are represented as two-dimensional porous surfaces in a model where flow is governed by Darcy's law, and heat transfer in porous media module is used for heat transfer. And lastly, the surrounding bedrock is modeled as a three-dimensional domain using, again, Darcy's law and heat transfer in porous media modules, allowing the interaction between the mine and the surrounding geology. And despite this simplification, the overall three-dimensional thermohydraulic behavior of the system is still captured in this model. So here the mine geometry is based on a real site, which is the Glasgow Upper Mine Working in this model, which is part of the UKGEO's Glasgow research site. We use this geometry because we did the validation of this modeling approach with this mine. So we continued with that in this study as well. But while the mine geometry is realistic here, the surrounding bedrock is simplified as a uniform layer. This is done intentionally in this work to allow systematic parametric analysis in later stages of this study. And lastly, here the well locations are also shown here, and they are placed approximately around 400 meters apart from each other to minimize thermal interference. So here we have boundary conditions and material properties. Starting from the boundary conditions, no regional groundwater flow is imposed here to allow the system behavior to be driven primarily by the injection and extraction processes. Initial temperature of the system is set to 12 degrees Celsius, representing the ambient mine water temperature. And as for the operational inputs, during summer, the heat is injected at a temperature of 17 degrees Celsius. And while in winter, the injection temperature is reduced to 7 degrees Celsius. And a constant injection and extraction flow rate of 11.5 liters per second is applied. And in the model, the simulation is initialized with summer storage cycle. And lastly, we have material properties summarized here. Because of the time, I won't go into details about them. So here we have the preliminary results of the simulation. So starting with the temperature evolution at the wells shown in the upper plot in here, we can observe a clear seasonal pattern corresponding to the injection and extraction cycles during summer and winter times. The warm well temperature decreases during heat extraction and recovers during injection, while the cold well shows the opposite behavior. And over time, these temperature profiles become more stable, indicating the development of a thermal plume around the wells. And to quantify them further, we have checked the thermal performance of the wells in the lower plot, which is the fraction of injected heat that can be recovered during the extraction phase. And as shown here, the thermal performance of the wells increases from approximately 43% in the first year to around 60% by year 10, indicating again a thermal plume development around the wells. However, due to modeling simplifications here, the system does not operate at its full capacity. It starts with around 72% of the target capacity, and it increases to 79% by year 10. This is mainly because the operation is defined using a fixed temperature difference in the model when determining the flow rates. However, in the model, as you can see, during the extraction, the heat extraction phase, this temperature difference decreases as the stored heat is also dissipating into the ground into the surrounding bedrock at the same time. So this reduces the recoverable heat and limits the effective system capacity. But in reality, this would require adjustments to operational parameters such as the adjusting flow rate or temperature based on the need. However, we kept them in constant in the model to observe the general behavior better. And here we have added small parametric study to see the effect of bedrock thermal conductivity on well thermal performance. So the baseline thermal conductivity was 2.5 watts per meter Kelvin, and this is varied by minus plus 0.5. And looking at the plot, we can say that variations in bedrock thermal conductivity led to limited changes in thermal performance overall. Higher thermal conductivity resulted a slight reduction in thermal performance due to the increased heat dissipation into the surrounding bedrock, and lower thermal conductivity enhanced heat retention, but it slightly improved thermal storage performance. So to conclude, in this study, we did a preliminary assessment of mine thermal energy storage system with seasonal injection and extraction over a 10-year period. The result here showed that thermal performance improves over time, starting from approximately around 43% to 60% by the end of the simulation. Due to the simplifications we have made, we haven't reached the targeted injection and extraction capacities, but the system operates approximately around 79% of the intended performance at the end. Bedrock thermal conductivity showed a limited effect within this investigated range. We didn't look up a wide range of thermal conductivities. That might be a reason as well. And higher values lead to increased heat dissipation and reduced performance here. So overall, we can say that these findings demonstrate that flooded mines have potential to function as viable thermal energy storage systems. So this was a preliminary assessment. In our future work, we plan to focus on different variables as well, different operational strategies, other material properties in the mine itself and the bedrock and hydrogeological conditions. For example, in here we didn't include the presence of fractures, which would be in this case more conservative approach. But if fractures are present, there will be a higher storage volume, and the performance might be better. So these things will be looked in future on long-term thermal performance of these systems. Thank you.